So let's take a minute to discuss, get our mouse out of the way. Let's take a minute to discuss this idea of the concerns of complexity with Rainscreen systems. Like I said, we continue to be in an evolution about the way we think about constructing wall systems. I've laid out a little bit of the history of the 70s of tightening up construction with air infiltration and then trapping moisture in buildings and the problems that came with that, and the idea of Rainscreen systems opening that up. And there's another problem that comes with the idea of opening up rain screens that is just relatively an event that happened. It's the Grenfell Towers in the UK. This is a building that had been reclad with a rain screen system. The cladding was a metal clad plastic panel, and that airspace between the panel and the insulation became a path for fire. So if fire started in one unit of the building, the fire started to escape through the window. The space between the glazing and the exterior cladding was a channel for fire to move up through. And because the panels were made out of plastic, it became a fuel source. And so the whole building became engulfed in flame. This was a huge tragedy. I have links to it so that you can go back and look at it. But it is it was rewrote the book about the kind of materials that we use in our rain screen systems. Remember before I was talking, well, you can make a rain screen out of basically any material. Well, today we would talk about any material as long as it didn't have flammability issues with it. And it's very easy in these ACM panels, these aluminum clad plastics and other materials, that the other material could be a flammable material. And it actually could be okay to be used in certain applications where there was no airspace behind it, where it couldn't easily contribute a fuel source to the building. But in this case, in that idea of rain screen construction, it did in a rather tragic and dramatic way. This caused not only the tragedy of this building, but all of the other buildings that were clad in that similar material had to be reclad and retreated in order to make them safe. And you can also imagine the tragedy of fire moving up the exterior of a building. We typically think of fire on the interior buildings, but now every escape window was now engulfed in flames. So it would have been a horrible experience to be trapped in a building where every window was on fire. So less tragically, but more of concern, this is just an analysis of a building that, or just my opinions on a building I saw under construction, and some things I want to point out about the way we're constructing wall assemblies today. So here we have, this is a part of a mixed-use development on Elmwood Avenue in the city of Buffalo. These are townhouses. These are actually at grade level with some outside patios. They're really nice. They're going to get a brick cladding veneer over them. So there'll be a space. You can see actually there's a placement of the first piece of limestone, a base stone before they put the brick on. And then we have the building. The silver is a exterior sheathing. It's actually an oriented strand board with an air and moisture barrier on the top of it. And you'll notice that it's taped at all of the seams. And the windows have that blue material, which is another waterproofing air barrier membrane that is adhered to that surface. So the idea, the sales idea of that, using that material, is that it seals everything in the building, makes it weather tight once you apply the exterior sheathing. That means you don't have to have the exterior, you don't have to apply any other material to the exterior in order to create that air and water sealing barrier. And so that's marketed as a labor-saving material. Now, what's really unusual, what really surprised me about that whole assembly is if that had been it, and then the cladding would have gone up, or the brick veneer, I would have thought nothing of it. But once they've actually sealed the building, they actually put another layer of insulation on the exterior of the building. And this could be obviously really good intentions here. We have a 2x6 wall construction. We can make that an R19. But if we add another 3 or 4 inches of polystyrene, if you look down on the corner, I think it says it's R7.3. We can really up the thermal performance. And it could be possible to meet energy code performances for this building. They were required to add some kind of additional insulation. The problem that I see is this is a double sealing of the building envelope. So here we have now that polystyrene going out. That is for sure an air and a water and a moisture barrier. Moisture can't permeate through those type of closed cells foams. And then you'll notice that they also have a sealing tape between them, so that lighter pink at the joints. And I have some close-up details of that. So here we have a window detail. Now we can see that that oriented strand board, and we can see some tears in it that I've indicated with the red arrows there. You can see the board beneath it and the foil or the metal, metallic looking surface peeled away from it. And you'll notice that it looks like it's not going to get any other treatment to it. And then you can see also the pink material going on and the pink tape sealing that. Now, my concern is that what happens if water gets between those two surfaces? Both surfaces are sealed, they're touching each other, so there's a great possibility of that mechanism we called capillary action moving and migrating moisture through that assembly and eventually bringing it to a weak point within the assembly, which could be where this wood is actually exposed. So I think their real failure here is in this kind of double sealing of that assembly so it can't breathe. And you'll say, well, they're going to seal everything up. There won't be a problem with it. No moisture will get in. But we can see many little construction details. For instance, this is that taping of those joints. And we can see here where the tape is starting to lift off. So it's not even actually sealing that corner of that metal or that plywood assembly. So any water that could get in there or move through that wall system, and this is an overhang area where there could be a roof failure, could be a place for water to migrate up behind there. So I suspect this system was going to perform fine for many decades. Any kind of water intrusion will be hidden. It won't show up. Any kind of mold growth won't be apparent, just as I showed you in the stucco systems. And so this will be a problem-free installation for many decades, maybe for a long time. It also could be a major disaster. If water started to get into the drywall areas and any mold grew, there could be all kinds of lawsuits and other problems with it. And I think it could be directly attributed to this kind of methodology of construction. And my question is are we engaging, our architects of this project engaging facade specialists, or are we allowing the contractor to be doing some of this level of detailing of the wall construction? Okay, so a little bit now, the kind of details that go into, especially terracotta assemblies. So here's a section detail of a wall. You'll notice once again we have insulation in the wall cavity where there's a chance for that to get moist, but it's detailed out. I think it's going to become pretty pervasive in the construction. But the specific reason of this illustration is to kind of show you what happens at that corner detail and to be aware of it. Many times we'll conceive that we'll have these perfectly sharp corners, and there are just technical things that happen with certain kinds of material. One of them is that you can't have a knife edge on that mitered corner because it'd be very susceptible to damage. So many times they back cut it. They take off so they have a 1/16 of an inch flat surface on it to create a more durable surface that can't become fractured. Because even though that may not look as nice as you want, what would look horrible is if there was a chip in those two panels as they came together. And once again, we have that capillary break, but that capillary break is also there because nothing looks worse than two panels that touch next to two panels that don't touch. It starts to look like a crevice has opened up that should normally be closed. So you want to try to maintain that kind of uniform gapping there. And then as this one illustrates, the other reason that we would want to have that is to allow for the thermal expansion and contraction of the components, which quite frankly in a ceramic assembly would be quite minimal. So here's another visualization. I think I have this hyperlinked. If you open up the slideshow of the attachment of panels, the exterior insulation, I think you'll notice that we're not seeing clearly delineated in this illustration that moisture barrier, the blue material that would go over the CMU unit, the air and moisture barrier. This is one by a manufacturer. just to show you the varieties of attachment and panel systems. You can notice actually some unique corner assembly there. So the outside corner has a re-entrant corner that is framed by an aluminum extrusion. And that's just to disguise the end effect of the panel systems that have open cells on them, and showing the interior details. So it's just a way to deal with that. So here we have some actual construction details. This is a building. I'm not sure what the building is. These appear to be Boston Valley terracotta tiles. This is on the Buffalo State campus of a terracotta new built building. So here we have that corner detail. It looks a little rough up close. You can see there's that line does not appear crisp. There's probably no way to improve on that in ways that could be controlled during normal construction. And then on the, let me make sure I'm saying this right. On the right-hand side, we have a window detail. We have a little piece of metal trim coming up. Once again, that's disguising or hiding the side profile of the terracotta panel. So once again, that idea of what the corner condition looks like, the one above my head there, you can see how they've got a flattened out surface. It has a little bit of a different kind of texture to it. These are things that would be common and ordinary and expected in the construction, but they might really be a huge surprise to you if you've been detailing these and are not prepared with working with the material. This is actually, I have mixed feelings about this window detail. It matches exactly with the coursing of the tile system, but I think that it is so small that the detailing of it, the returns and flashings, really become a little bit clumsy looking in it. Another reason to just kind of consider the size and scale of the elements that you put in, and then what their final appearance might be like. I just left this in. This was on the same campus. This is another kind of facade system. I was just fascinated by the idea that that looked like the facade had drawers on it and they were being pulled out of the facade or the face of the building. The internet's full of examples of Rainscreen design systems, panel systems, and attachment systems. I think that you can review these and you'll find a lot of consistencies between the way panels are attached and the differences in the early stages. Once you've made a plane for the panel, anticipated the use of a clip system and an attachment girt and an air gap and then an insulation layer, changing out systems depending on value engineering and material selection by your client would be easy changes for you to make. This is Boston Valley. This is the kind of detail that Boston Valley provides for clients, architects, in order to detail out their systems. And I've used these in order to create the master panel system that we're going to use in our project. So that pretty well completes the lecture portion of the Rainscreen project, and hopefully sets you up to enjoy and gain a lot of knowledge in working through the module of the project that we're going to do this week or in this module.